Hey there, pre-calc friends. At the beginning of the year, one of the things we talked about in terms of fun projects for Chapter 3 would be becoming archaeologists. And that's what we're going to do now. We're going to find out how to date some fossils that we find, figure out where they came from and when they came from. But in order to do that, we need to learn something that's called carbon dating. What they use is they use the element of carbon to figure out, given a fossil, if you know how much carbon is left and how much you started with, you can pretty much figure out how old that fossil is. And we use something that's called half-life. So we're actually going to start with half-life first for this project. The half-life of an element is how long it takes in time for it to become half of what it started to be. So whatever its starting mass was, when it becomes half of that, as it decays, how long did that take? And that time is called the half-life. And then after another half-life, you have another half of that. And it just keeps halving and halving and halving until it gets smaller and smaller. So we have a couple of elements over here in this chart, a couple of isotopes that are radioactive, and so they're unstable. And so after a certain amount of time, you're only left with half of the amount. For example, if you look at a americium here, this has a half-life of over 432 years. So if we start with 100 grams in the beginning, after 432 years, you will be left with 50 grams. So all of these half-lives are how long it takes for a certain element or isotope to become half of the amount it started with. Okay, so we need a formula for this, and we just happen to have a handy-dandy one here in the chart. This is what's called the half-life formula. And if you take a look at it, the cool thing is, if you notice, the exponent of time is there. It's in the power. So this guy is an actual exponential equation. So we're going to be solving these exponential equations like we've been doing in class, using the ln, using the logarithms. So what we have to do in this first page is, you're going to be given a certain isotope, and you have to find out which one it is. But all you know is, how long have you had it for? How much did you start with? And how much do you have now? And notice that the starting amount here is always larger than the ending amount now. Which makes sense, because as these are decaying, they should become smaller in mass and smaller in size. So the starting amount should always be larger than the ending amount. Okay, let's label a couple things here in our formula. This, A sub 0, that is your starting amount. How much did you have before? There was how much? The A here is sort of your final amount. This is how much you have now. After a certain amount of time passed, after a certain amount of decaying happened, how much do you have now? This is almost like compound interest. Do you remember? The starting amount was how much you deposited, and now how much money do you have after compounding for so many years? Same idea. A sub 0 is the starting amount, the starting mass, however long ago it was, and now how much are you left with after all the decaying? Okay, you are multiplying by a half every time. That's why it's called half-life. So your base here is always a half. The base is always 1/2. And 1/2, as you can tell, excuse me, is the number that you're raising to a power. You can see the t over h as the power. Well, let's talk about that t over h. T is always time. How long have we had this element or isotope for? But h is really the important part. H is the half-life time. So how long does it take for this element to exist before it becomes half of the amount that you started with? So t is the time that you just measured it. It was in there for 1.5 years or 10 years. But I know the half-life is like 2,000 years. So how can I use that to figure out how old something is? Okay, so let's look at number 1. Our goal is to use all that information to go back up to the chart and determine what is the half-life of number 1. And therefore, if we know what the half-life is, if we know what h is, so we're solving for h, can we figure out what element it is? If we know what the half-life is, we know what this mystery element is, can we figure out what it really is? What's the name of this element that we figured out? Okay, so first of all, let's plug in everything we know. So let me erase all this stuff here. Let's just start with number 1 element, whatever isotope number 1 is. All right, we have A equals, and A, like we said, is the present amount. How much do we have now? And that's what's right here, the 99.39. So that's A, that's how much now, equals A sub 0 is how much you started with. Remember in the question it says originally there were, and we said that the original, the starting amount, is always larger because these elements decay. Times, the base is always 1/2, and you're raising it to the t over h, the time. How long did you have it in for? There's the 1.5. And h we don't know, because remember friends, h is what we're trying to solve for. What is the half-life? And it makes sense because you look at this equation right now and the only variable you can play with here is just h. So we need to take this friend and solve for h. So again, the variable is in the exponent, so we're going to have to eventually use logs to solve for them. Okay, well maybe we can find a little bit of a shortcut here. I'm going to take a break for a second, and can I just play with this for a sec and just solve this for h? Because if I can solve it for h, then we can use it for all of these isotopes in this entire page. Now I don't have to keep rewriting these equations. So let me go back a step. Let me go back to our title page here and just play. Okay, the equation was A equals your starting amount times the base, the half-life base, of t time divided by h. Okay, my goal right now is can I solve this for h? Because if I can solve this for h, then we can go back to our previous page and just start plugging in and solving for h right away. Okay, so we don't have to redo this equation manipulation every time. Well, like we've learned before, friends, we're going to use logs to try to break apart this exponent and bring him downstairs. But I can't do it yet because there's something in the way of the base. Can you see? He's not by himself. I always need to divide the starting amount on both sides first. So first step, let's take a sub 0 and divide it on both sides. Okay, now I can see the base of 1/2 is all by itself. Great. Now, since it's all by itself, can we bring in the logs? Oh, you betcha. So let's ln both sides, and we get the ln of the whole left side, the present amount divided by the starting amount, equals the ln of the other side. Great. Okay, now that we're in log land, yay, now we're in log land, our log law says that this power is free, so I can put him in the front. All right, so here's what we get so far. ln of the left side still, great, equals, all right, the t over h goes in the front, times the ln of 1/2. And remember guys, as we're playing with this, ln of 1/2 is just a number, right? Because 1/2 is a number, and if I take the natural log of a number, I get another number out. So this is just a number. So if we need to like move it around, just treat it like it's a number. All right. So our goal is to try to get h by itself, and h is kind of hidden down here, right? Well, don't worry about it. Let's see what we have on the outside that we can undo. And I see I have this, the 1/2 ln. So it's multiplied. How about we divide both sides by that? Let's see what happens. All right, so I'm going to go over here. Let's divide both sides by the ln of 1/2. And I get, on the left side, I get ln of a over a0 over the ln of 1/2. Boy, this is looking messy, right? Oh my gosh. But we can do it. Equals, on the right side, now that the ln is gone, I just have t divided by h. Oh, sweet. Now, there's different ways to get the h by itself, guys. If you ever have a fraction equal fraction, if you remember from your algebra days, you could, if you want, do this. Do you remember cross multiplying? Cross multiplying is great. If you want to multiply diagonally across and set them equal, you can solve for h. Or another way to do it is if t over h equals that left side, I can flip this side as long as I flip this side. That's fine too. Honestly, I like the cross multiplying way because it takes me back to my algebra days. So what I'm going to do is I'm going to do the cross multiplying. Ready? That comes up here. When I cross multiply, I'm going to multiply diagonally. So the h is going to multiply the ln of a over a0, and that equals the other diagonal multiplying. So that's going to be equals t times the ln of 1/2. Do you see how I did that? That's just cross multiplying. When you cross multiply, you multiply diagonally, you set them equal to each other. All right, I'm almost done. Look at that. I just need H. H is almost free now. The only thing that's in the way is this. So why don't we just divide both sides? And here comes your magic number, friends. Ready? H equals T, the time, times the ln of a half divided by the ln of A over A0. Okay. So the reason why I did that is because in this next page, when we come back to it, our goal was to solve for the half-life, right? That was the question. Can you solve for H? And then can you figure out what the mystery element is going to be based on the chart over here after you solve for H? So isn't it much easier now? Instead of using the half-life formula we were given, we kind of played with it, moved it around, and why don't we use this formula now? That might be a little bit easier just to plug in and just do some calculator action. Okay, so here we go. Let's try the first one now using our magic formula that we have here for H. All right, so let me make a little bit of space here. Number 1. Okay, so we got isotope number 1. We need to figure out the half-life. It's been kept for 1.5 years. That's our T. Originally, that's your big clue. So that means that must have been my starting amount. And then now, presently, now, that means the A. Okay, I think we have everything we need. All we got to do is solve for H. So again, I'm going to bring my formula back up here. H equals the time times the ln of a half over the ln of, and I believe it was A over A0, right? Yep, A over A0. Okay, so let's plug in everything we know. This really is, I'll use this next box down here, sorry about that. I'll use 1.5 as my time times the ln of a half over the ln of, okay, my final amount, A just itself over here, the final amount, which is always smaller, is 99.39 over A0, the starting amount, which is always bigger, 100. There we go. So we're using logarithms to help solve the half-life formula into something a little bit more manageable. But now that we have this magic formula, now we can just plug it in. Okay, so here we go. Now I'm just going to plug this into my calculator and see what we get. I'm doing 1.5 times the ln of 0.5 or 1/2. And after that, I'm going to hit enter. Okay, I get like negative 1.04 or so. Now I'm going to divide, hit divide symbol, and it uses my answer button. Divide by the ln of 99.39 divided by 100. And those numbers are both inside the logarithm. Close my log, and I get right here, let me erase it because it should go into this space here, my half-life is equal to 169.9. That means this isotope number 1 takes about 170 years to lose half of its mass. So after only 1.5 years, you can see that it went from 100 to only 99.39. Oh. If it went for 170 years, we'd be down all the way to 50 after 170 years. But we only went 1.5 years, so it makes sense. I didn't really go down that much. Okay, so that was just calculator action. That's not bad. So I get about 170. So what we're going to do is take your eyes up to this list up here, and can you find the element that has a half-life of about 170 years? Found it right here. So what is your mystery element? Your mystery element here was silicon 32. Great. I don't want to do the last column when there's going to be 1 gram left. I don't really care. I don't want to do that. I just want you to work on, can you plug in using the half-life formula, and in fact using the brand spanking new formula that solves already for the half-life, calculator, and then can you figure out what the mystery element is? So number 1. For number 1, the answer is 170 years for the half-life. And what's my mystery element? Looking back up to the chart was silicon 32. So for the rest of the chart here, friends, all you're going to do is plug it into our magic formula that we have now using time, looking at the starting amount and the final amount. And the rest is just, like I said, all calculators, folks. Okay? After we learn how to do that, we're going to only stick with one type of isotope, and that's carbon. Carbon is a great thing because it's used in it's found in a lot of living things, a lot of organic material. So we can determine if we already know here the half-life of carbon. Look at that. They already gave us H. Based on that and our new formula, we can actually carbon date a lot of these fossils here, like a cloth, like a shield, like a sword, like a dress, and try to figure out, if we know how long the half-life is, can we figure out where it comes from on our timeline. So that's going to come up next. But for the first part, folks, your challenge is, can you fill out this chart and figure out all these mystery elements? Again, skip the right-hand column. We're not going to do these for these problems. Sounds good? All right, my fellow archaeologists, good luck. See you next time.